In this video, I will be demonstrating and explaining something known as the Collatz Conjecture, or in this case, I'm referring to it as the Collatz Algorithm. First thing I want to talk about are algorithms in general. And I thought a nice example might be to use Michael Pollan's eating algorithms. Now, Michael Pollan is a fairly well-known author. I think he also has a show, a cooking show on Netflix. I've heard about. I haven't seen it myself. He also wrote a book that I've read several of his books, but his latest book, I believe it's his latest book, it's a recent book, is titled How to Open Your Mind. And this book is all about hallucinogenic drugs and their use for treating certain types of medical disorders, things like LSD and so if you like to read this, I found this latest book of his very interesting. And one of Michael Pollan's kind of like methodologies is that he likes to try things and then write about it. So I won't be a spoiler, but just know that often what Michael Pollan does is he actually experiments on himself and then writes about the experience. So fascinating book, How to Open Your Mind. But that's not where the eating algorithm idea came from. There was a point in my life where I was close to 300 pounds and really decided that I needed to lose weight. And so these eating algorithms are the method that I chose to diet. And it worked for me. And I think partially maybe it worked because my mind, I'm a mathematician. I've been trained to think often in terms of algorithms. And basically, Michael Pollan has a list of what he calls eating rules. For example, avoid food products containing ingredients that no ordinary human would keep in the pantry. Avoid food products that contain high fructose corn syrup. That's a hard one to do, but not impossible. And what I found with that rule is a lot of the unhealthy food that I was eating, that rule just eliminated right off the top a lot of really high calorie fattening foods. So for me, that was a good one. Avoid food products that have more than 5 ingredients. Avoid food products containing ingredients that a third grader cannot pronounce. Don't eat anything your great grandmother wouldn't recognize as food. If it came from a plant, eat it. If it was made in a plant, don't. Eating what stands on one leg, mushrooms and plant foods, is better than eating what stands on 2 legs, fowl, which is better than eating what stands on 4 legs. So in Michael Pollan has, I think there are like 52 of these rules. So you can look it up on the internet if you're interested by Googling something like Michael Pollan's eating rules. So anyway, this is an algorithm. This is an algorithmic approach to dieting. You know, when I look at a piece of what might be called food, I apply this set of rules. Would my great grandmother recognize it as food? Cheetos? Maybe not. You look at the ingredients on a bag of Cheetos, and I'm pretty sure you might find high fructose corn syrup. Certainly, that I love Cheetos too. By the way, I'm picking on Cheetos, but I don't eat them anymore. But I like them. But in any case, this is the point. And red meat, cutting that way down, all of these things. So algorithms, an algorithmic approach to eating. So let's talk for a minute about the Collatz algorithm, which leads to something known as the Collatz conjecture. In mathematics, we call something a conjecture if it has not been proven using mathematical techniques. And so the Collatz conjecture is not yet proven. So I'm going to write this in a special kind of a math notation. This is a notation we use to write sequences. So we're going to take the number, the next number in the sequence, that's what the n means, is going to equal the previous number in the sequence. That's where the n minus 1 subscript on the a, what that means. We're going to divide it by 2 if that number is even. And we're going to multiply by 3 and add 1 if that number is odd. And this definition of this sequence is in other parts of the course material, so you can find that some other places. So what we're going to do is start with 11. And the other thing I should mention is that all of these numbers, all of these a's are natural numbers. And the natural numbers are a set of numbers. Let me write down the set. Starts with 1, 2, 3, 4. Dot, dot, dot. The ellipsis means continue in that pattern forever. So this is an infinite set. So 11 is a natural number, comes from this set. So we'll start with 11. Now 11 is odd, so we will multiply by 3 and add 1. So that's 33 plus 1 is 34. "34 is even, so I'm going to divide that number by 2. 30 divided by 2 is 15. 4 divided by 2 is 2, so 15 plus 2 is 17. Oops, try to make that legible. 17. And then 17 is odd, so we multiply by 3 and add 1. Let's see, 3 times 7 is 21, plus 30 is 21 plus 30, that's 52. Now, one thing I'm going to do also is I'm going to show you how to do these on the calculator as well. Because we can do the arithmetic, certainly. We could, sometimes actually the arithmetic, depending on the size of the number, can be quite difficult. So 34, that was correct. And then, let's see, let's do 3 times 17 plus 1. That's 52. 52 is even. So I'll divide by 2. I'll do a couple steps at a time. So we're going to go 52 and then 26. "26 is even. I believe 13 times 2 is 26. So let's see, I'm going to take a chance and do this one in my head. So 3 times 13 is 39, plus 1 is 40. 40 is even. Divide by 2, we get 20. Divide by 2, we get 10. Divide by 2, we get 5. 5 is odd. 3 times 5 is 15, plus 1 is 16. Divided by 2. Divided by 2, divided by 2. I'm going to run out of room. 1 down here at the very end. So this is what makes the Collatz conjecture so interesting. It turns out that every natural number that's been tried, and many, many, many of these have been tried, always results in a sequence that comes down to 8, 4, 2, 1. We'll try this with some other numbers as we go along. Now, this is a relatively simple computer program. that I wrote that will do the calculations for the Collatz conjecture. And what I'd like you to do is get your calculators, um, and I'm going to go through all the steps to enter this program. It'll take a few minutes, but I think that having this program will be a really fun thing for you to enjoy with you and with your friends. And I'll tell a little story about how I had a fun experience with some of my friends regarding the Collatz conjecture. But for now, let's stay focused on programming, entering this program into the calculator. All right, I'm just going to move my calculator over here. All right, I like to clear the home screen. You don't really have to do that for what we're going to do next, but it's just kind of a habit of mine. So here we're starting with the very beginning. So locate the program key on your calculator. It's right here, kind of in the middle of the calculator. PRGM stands for program. Press that key and this will bring you into the program menu. And you can see I have a few other programs that I've written. And those are actually programs that were part of the first quiz. So when we want a new program, so I'm going to arrow 2 to the right and select Create New. Now I need to give the program a name. The calculator is prompting me for a name. And notice the cursor right here. There's an A inside the cursor. What that means is that the calculator is in alpha lock mode. And so if we type the keys, when we type a key, the calculator is going to type the letter corresponding to the key. So I'm going to call the program C O L T Z. Now, I know I'm not spelling Collatz correctly, but the calculator will only allow 5 characters. As a matter of fact, it looks like 1, 2, 3, 4, 5. It looks like the CE is maybe allowing me to have more characters for a program name. Maybe I was wrong about that. So let's see if I can spell out the whole name. See what happens. Okay. If you're using a previous version of the calculator, like a TI-84 or a TI-84 Plus and not a CE, I think you might be limited in how many characters you can put into the program name. Okay, now we're going to press Enter. So we actually have just created this program. There are no lines of code in the program yet, but there is now a program in the calculator called Collatz. Now, the first part of the program here, these first few lines, this is just going to get printed onto the screen to explain to the person using your program what the program does. DISP stands for display. Let me show you where to find that command. Look under Program, and IO stands for Input Output. And under the Input Output menu, we've got several different things, but the one we want for now is Display, number 3. And a shortcut for accessing that command is just to press the 3 that corresponds. Now I'm going to alpha lock the calculator. I'm going to go second alpha, and see there's that A coming back. And that just will cut back on pressing alpha over and over again, because everything that I want to type right now is alphanumeric. The space is kind of a weird thing right here. That little, I'm not sure, how to channel looking kind of symbol. I'm not sure what to call that right there, but that's the space. So press a 0 to get a space. And then we must end it in quotes. So the quotations tell the calculator that this just is going to get printed out as is. Now press enter to go to a new line. Same thing, go to program, IO, choice 3, second, alpha to alpha lock. Close quotes. And please keep in mind, if I go too fast, you can always pause the video and back up to see a step again. And I suppose if I'm going too slow for you, you could always skip forward. You can go forward and backwards, I suppose, if you want to. Now, this next line here is just an empty set of parentheses. And what I want to do with that, the reason I'm putting that in there is we'll have a space now between these sets of, this text. And it will make it easier to read when we actually run the program. So I'm just going to do a double set of quotations there. And then this next part tells the user what they should do, which is important, I suppose. Remember, the zeros corresponds to the space. Now for this next phrase, natural number, I'm not sure if this will fit, the whole thing will fit on the TI-84 screen. One of the things with the CE version, the newest version of the calculator, is the screens have more pixels across. There are larger screens and they have more pixels, so they can fit more characters across the screen. I'm going to go ahead and what am I going to do? I might just write this in 2 lines of code instead of 1. If you want, it looks a little better, I think, on the screen to have it all together in 1 line, if it'll fit. Let's try it this way first. So here I am modifying the program on the fly, which isn't always a great idea, but I'm gonna risk it. So we'll see what happens. All right. But if you're using the CE calculator, you could just put natural number on the same line there. All right, so the next thing, now these first 6 or 7, 8 lines of code, this is just what we call documentation. This is just, again, The calculator isn't doing any like calculations or anything. It's just printing that out. So the first thing we're going to do is we need to have a number inputted into the calculator. So what prompt means in this computer language is that the calculator is going to print the letter. In this case, we're going to use n as our unknown, and then I'm also going to display n. And basically, that's just to make the output look right. It seems, I know, probably seems a little odd to input in and then immediately display it. Now, LBL stands for label. And what we're going to do is create something called a loop. I'm going to show you how that works here in a minute. So label 999, not 999. Let's keep it at 99. And what that's going to work with is this go-to statement. So when the calculator goes down through these lines of code, if n is not equal to 1, then the calculator is going to go back up here to 99 and repeat. And notice we're storing each time the new value is n. So each time we'll have a different n, and that'll be the n that would be part of the Collatz sequence created by the Collatz algorithm. Let's see, program if-then statements. So basically what we're saying is if the f part, now f part you find under math, then arrow over to num. This is, we can take a decimal number, we can break it into two parts, the integer part or the fraction part. So f part stands for fraction part. So if we take an even number, I'm sorry, we're doing odd first. I have them kind of reversed in the computer program, I guess, compared to how I wrote them before, but it doesn't really matter. So if we take our number from the sequence we're generating, oops, not a log, hold on now. Try that one more time. I need the alpha n and divided by 2. Now, if that number is odd, there's going to be a remainder of 0.5. So we'll go to second, math. It's where we find that equal sign. And then this colon acts like the then. If this is true, the fraction part of n divided by 2 is 0.5, then take the number, multiply it by 3, add 1, store that back into n. If, on the other hand, the fractional part of n divided by 2, now we know if the number's even, that there should be no remainder when we divide by 2. So 0, the fractional part would be 0. And if that's the case, then we're going to take that n and divide it by 2. And then store that back into n. And we're going to display each one of these n's. So we go back to I/O for input output, choose display, n. So one more if statement. We have to know when it's going to stop, and I'm relying on the truth of the Collatz conjecture to have a stopping criteria for my program. If we ever hit a number where the Hailstone, or sometimes the Collatz conjecture is also referred to, the sequences that it generates are referred to as Hailstone sequence. If there's one that doesn't converge to 4, 2, 1, then we would have a problem with this line of code. But so far, I've used this program and not had any issues with that. We need a not equal to this time. And then our colon. And then go to, which again is back under the program menu. I think it's next one after label. And the final thing we need is to tell the calculator to stop. All right, that is the program. Now let's run it and see what happens. So to run the program, I'm going to just go back to the program menu. Oh, wait, I'm sorry, I have to quit. Hold on. All right, second quit first. Then go to the program menu. There's our program, Collatz. So I choose it. Now at this point, the calculator hasn't actually executed the program. It's waiting for me to tell it to execute the program. So I just simply press enter again. Pick a number, pick a natural number. How about 44? If you want to run the program again, just press enter. Let's see, let's try 9,075. Amazing. Let's try a really big one. Now, I said I was going to tell a little story, and here's something that I found really interesting. I was in a car on a car drive with some friends, and these were actually friends. Were not math. These were not colleagues or necessarily people that were math teachers or anything like this. Just some of my friends. And we're driving along in the car, and I'm talking about this Collatz conjecture. And I had just written this program. I had it on my calculator. And so I ran the program, and I told my friends, go ahead and put a natural number in there. I had to explain what a natural number was. And so they started to try these things, and it was really, they were amazed. And it seems to be true for all natural numbers. And so I asked my friends, I said, okay, well, does this prove Collatz conjecture in your mind? And a really fascinating debate ensued. Some of my friends said, yes, this proves it, convincing, without a doubt. But then some of my other friends were like, well, wait a minute. To prove something, don't you have to try it for every single number? And if there are an infinite number of natural numbers, that would be an impossible thing to do. And so we had this really interesting discussion about the difference between proving a conjecture in mathematics versus finding evidence that makes us confident the conjecture is true. So as a mathematician, what I would say is, this conjecture has not been proven. And if you watch the other videos this week, you'll notice that one of the professors that studies these types of things, a number theorist, he wonders if mathematics is ready to prove this theorem. So anyway, I hope you enjoy this video. I encourage you to share this program with your friends and family members and your children. I think that this is something. Sometimes people wonder how can mathematicians get so into mathematics, and I think sometimes people fail to realize that mathematics isn't really about computation. It's not really about adding and subtracting and all of that kind of stuff that we do all the time. This is what really interests the mathematician, or a phenomenon like this. Every natural number we try does the same exact thing, and I can just, again, I'm just kind of hitting the keyboard with different numbers, just, I don't even know how big I can go here. I'm just playing around with it. And this is wondrous. I mean, the amount of computations the calculator's doing really rapidly is pretty amazing. And there it is, 8421. So I hope you enjoy this video. I hope you have fun with the program. Please be sure to message me if you have any questions. Have a great day.